Good morning, everybody. Welcome to today's Strategic Farming Let's Talk Crops program. We're happy to have you join us today for today's program. The topic of today is modeling how management impacts soybean growth and development and yield to help farmer decision making. These sessions are brought to us by University of Minnesota Extension and generous support from the Minnesota Soybean Research and Promotion Council and the Minnesota Corn Research and Promotion Council. My name is Angie Peltier. I work for University of Minnesota Extension as a regional crops educator in Crookston. And I'd like to welcome today our guests. We have Seth Nave. He's a professor and soybean agronomist for University of Minnesota Extension. And Anibal Cerudo, excuse me. He's a visiting professor from Argentina who is working currently in the Nave lab. Just a couple of housekeeping items before we get started. These sessions are meant to be relatively informal and more of a discussion. And our speakers will start out the morning by presenting information on the topic at hand, and then we'll open up things for your questions. So the discussion will also focus on questions that we received while you were registering. So thank you for those questions. Meanwhile, please insert any questions you might have into the Q&A box at the bottom of your screen. If you're not familiar with Zoom, hover your mouse near the bottom of your screen, your Zoom screen, and you should get a toolbox to appear. On this bar, you'll see the Q&A box. That's where you'll enter any questions you have for our speakers today. There's also a chat box. Please reserve that for technical issues that you might be having. Also note that we will have a three question, very short survey that will pop up automatically when you go to log off of Zoom today. Please fill out that survey. We really value the information that you provide to us. Each session will be recorded and will be posted at a later date on the website if you missed something. Also, please note for those crop advisors in need of continuing education units, right at the end of the program today, we will have a QR code. So you'll need to use the CCA app in order to scan that QR code to obtain a CEU for your attendance here today. With that, I will turn it over to our speakers, Dr. Seth Nave and Anibal Cerudo.
Good morning, everyone, and welcome to this grand experiment from the Nave lab here today. Again, Seth Nave, and I'm a soybean agronomist. Angie approached me, several months ago and was mentioning something about some of the modeling work we were doing, and she was kind of interested in this, and so we proposed this as a topic for today's session. I think it actually works quite well for this kind of a session because my feeling is that there's a lot of people out there talking about AI technologies and about, broadly, and then about things like modeling for climate or in our perspective here in terms of crops. And I think there's a lot of talk about it, but nobody's really discussing any of the details because it's very easy to get really deep into things. And as scientists, a lot of us tend to just go right to the too complex piece of this, and there's a lot of folks that don't really have a good handle on what models are or what they can do, and is this something that's important for the future? Is this a tool that we could use or not? Is it just for scientists or is it just for farmers, or how are we going to use these things? So Anibal Cerudo has been working in my lab for the last 3 years. He's a visiting professor from Argentina, and he's really elevated the type of work that we're doing. I do a lot of very classical and highly applied work. There's some good modelers around, but I haven't connected with them very closely on crop modeling for soybean. And so Anibal really brought those tools to our lab, and so he's been doing a lot of great work with us. I will go ahead and start my presentation now. And I think if we go to the next slide, Anibal and I are managing the AV here. And so I'm working back and forth with he and I to try to get the right slides up for you. So this is an image of our lab. Most of the folks, Anibal isn't in here, and a postdoc in my lab is not represented. We also have there's there's 6 students as well in this image, so we have a pretty large lab. But Anibal and I have been really fortunate, and we've had really good funding from Minnesota Soybean Research and Promotion Council. They've noted the skills that he's brought to the lab, and he wrote several proposals for our lab, and so we're doing some really interesting things beyond some of the things that we've done in the past, including some of this modeling work. And so that's what we're here to talk about today. And I just wanted to get another thank you out to the Minnesota Soybean Research and Promotion Council for their support here. So let's go into one other introduction slide. Really and I think the way we're going to handle this today is of course, I told Anibal that he and I would share this presentation, and then as this thing got put together by Anibal, I basically backed out and said, well, why don't you just do the whole thing? And so we're compromising in that I'm going to give an introduction, and Anibal is going to give most of the presentation, and I'm going to jump in with a few comments here and there. And if there's anything that I think that might need clarification from a real applied perspective, I might jump in on some of those things, but we'll keep it going that way. So just in terms of models at a very high level, what we're talking about is we're talking about bringing in data from weather, soil conditions, basically trying to identify the environment as a whole, latitude and longitude, genetics, and then the soybean varieties that we're putting out there, or any crop variety, is important to tune these models. And then management on top of that. And what comes out is ideally we get an estimate of crop yield. So you could imagine that this could be a tool for researchers to do a lot of work with and help them expand how they do research. But it's also could be a tool for producers. And we've seen some folks dabble in this at the corporate level. We've seen Climate.com and Corteva's products and Syngenta's products that all do something a little bit different for farmers, local tools as well to help farmers. And what we're talking about is kind of a research side of it, and trying to develop more specific open source resources that all farmers could utilize. And I think that's where the soybean checkoff comes in, is to develop things that are outside of these proprietary tools that could be utilized by farmers. So with that, I think I'll turn it over to Anibal, and he can give some more details, maybe back up a little bit of these introductions, and then move on into the presentation.
Okay, Seth, thank you. I think that the introduction was great. So we are going to try to see how crop modeling or crop models are useful for taking decisions, and you mentioned the most important part. So ideally, with the model, we can create, like, virtually a crop, and we can have a result. So without risk, we can assess a crop under different conditions, and then we can decide what to do in a real condition in our fields. That's the very short story of how we should, or we can use modeling as a tool in agronomy or in managing our fields. So we are going to go deeper in not too much, but we are going to go deeper in modeling, and we have to identify different kinds of models first. So we have 2 main types of models. We have the mechanistic models, are the process-based models, and we have the data-driven models, the AI-based models that Seth mentioned before. And so very simply, we can find big differences in between these 2 models that are going to give us the strengths and the weaknesses of these 2 types of models. And the mechanistic models, the process-based models, as the name says, are built on understanding processes. what is happening in a crop, how the crop is growing, how the development is going on in the crop, how the water is moving the soil, how the nutrients are being uptaken by the crop. So we have a lot of equations working together, sometimes complex equations. And this brings that we need a lot of data to run these models, for example. And on the other hand, we have the data-driven models. And instead of being based on knowing the processes, they learn from the data. They try to find patterns or relationships from the data set without asking what is going on there. But if we can find a pattern, we can predict what's going to happen under a specific condition. That's the idea. So they are very different. And because of these differences in how they work, we can, if we have so we can start thinking what can be a strength of one and a weakness of the other. And because the mechanistic models are sustained on knowing of processes, we can say that one strength is that they are more explainable. So we know what is happening. We can check. We have like control checks within the model because we know the processes. We know what to expect from a process. And this allows us to generalize the results, go to other scenarios, extrapolate the model to different conditions. We have to validate the model anyway, but that's the strength comparing to the data-driven model. And the big weakness is that it's very complex. We need to obtain so the data that we need to input in this model are very hard to obtain sometimes, and you need a lot of expertise to use this kind of model. The prediction can be very accurate, so we have to say that. So then we have the data-driven model. The strength is the opposite. They are showing us that we don't know what is happening in the crop to predict the yield or the output of the model. So this is the strength. Sometimes it's useful because we don't know what is happening, but maybe the data are showing us a pattern that is going to be useful for us to predict what is going to happen under a condition. And the big weakness of this kind of models, and because of this, or because of this, how they are working is that they lack of transparency. So we don't have this intermediate checks to see what is going on. It's like a black box. So it's really hard, or maybe we can't generalize or move with these models to a condition in which the model was not trained. So because we can have like a really unexpected or wrong result. So that's the two big differences in between mechanistic models and data-driven models that sometimes nowadays we are going more and more data-driven models. So this, if you can go deeper, then we have tools now to easily ask internet and check the differences in between models. But in the lab, we are working with both kind of models. But for this presentation, I will continue with mechanistic models. We are going to go deeper with mechanistic models and try to see how they can help us and why we are working with these models, thinking in Minnesota systems.
Yeah, and I'll jump in and just throw out kind of a real kind of a low-level explanation of these AI models. And in some ways, they run on simple correlations in a big way. It's much more complex than that, but I think that's the way I think about these in a lot of ways. It's correlations with things. And so you end up, as everybody knows, you end up with all these kind of spurious correlations can show up. There's all these classic examples about, storks populations and babies being born. These aren't causal relationships, but they're actually, if you put stork populations into a model for births, you'd actually end up showing that this is a predictor of how many births you'd have it was in Holland, I think was the particular example. Or there's a classic example of football, the Redskins actually predicting presidential wins. 16 presidential wins in a row were predicted by wins by the Washington Redskins. So if you put Washington Redskins into a model that's predicting presidential wins, it would have shown that as a big driver of influential piece of this. So the good thing is that these things tend to work, but the bad part is we don't know why some things work and why some things don't work, and it's very difficult to decide what data to input into these big AI models, because sometimes that data can lead you astray, or you can have these spurious kind of correlations or drivers that don't actually, they've been historically predictive, but as we move into the future, they're not very good for us. So I'll let Aníbal take over from there.
It was a really nice example. So let's continue with this. The idea is now to see how a mechanistic model works, and then we are going to try to use two concrete examples of management practices to see the utility of modeling in our systems. So this is a very, very simplified scheme of a mechanistic model. It's very simplified, but it's still complex. I think that for most of you, it's still complex to see this, but this is the important thing. Processes. We have processes in colors. So it's yellow, orange, green, and blue. These are the main processes that this model is trying to describe in a crop. And we have the development, how the stages are going to happen during the season. We have the growth, that is the accumulation of biomass. We can think that photosynthesis is going to be a big part of this green box. Then we have the partitioning. So it's how the biomass that is being accumulated every day is partitioned between the different organs. And this is going to be important because we are mainly interested in yield. But if the partitioning is wrong in the model, then the amount of biomass that is going to the leaf or the roots is going to be wrong. And then it's like a feedback for future growth, because, for example, if the model is predicting that the leaves are smaller, then the ability to capture radiation is going to be wrong. So the growth for next day is going to be wrong. So everything is connected and must to be almost perfect to have a good prediction with equations of what is going on in this crop and how biomass is being accumulated and distributed among organs. The only thing that we want at the end is yield, mainly in the field. So, for example, let's try to. So I forgot to mention that these processes are governed also by the weather, the soil, and the crop management. This is the most important part. And for example, development. You can see that the weather is going to be the one of the major drivers for development. Photoperiod and temperature, for example, are going to be the drivers. Then we have growth. Radiation is going to be really important there. And then temperature affecting the radiation use efficiency is going to be important as well. I can use this. Sorry. So everything is connected. Water and nutrients that are going to be dependent on our nutrition management, the rains and the soil, different soils, the water table, everything is going to be. We need to describe everything, all the relationships that are going on in between plant, soil, and nutrients, because this is going to affect how the leaves expand, how the radiation can be transformed in biomass. Everything is connected. So what these models are trying to do is to connect all these processes, and if they succeed in that, then we can check how changes in weather, soil, and crop management can affect yield. This is ideally, if everything is working and all the processes are well described by equations, by knowledge, so we can arrive to a good estimation of yield. And now let's try to, so it's not important to understand all these processes to follow the talk. So I want to show that what we are trying to do is to describe processes and try to connect them. This is what models have been doing since the 80s, I think. So the model that we are going to use is from the 80s. We have more recent models, but every model is evolving. So because we are learning, so every one of these boxes is changing every year. So as we learn, as science gives some feedback to the processes, everything is changing and it's evolving, and our capacity to predict is increasing as well. So let's start with the first example, where we think that we can understand how crop modeling can be useful for us. And it's planting date, one of the most relevant management practices and one of the more stressful management practices. So when to plant soybean. And if we want to know, as for every management practice, if we want to know when to plant, we need to know the yield response to planting date. If we have the yield response to planting date, then we are going to be able to see how many risks do we want to take, pushing the planting date too early, or we can decide when to kill the cover crop. We are thinking, for example, in cover crop biomass. So we need numbers. We need to put. We know that planting date is going to be depressed as we delay planting date, but we need to put numbers to this relationship to incorporate this to the discussion and to compare or to decide finally when we are going to plant. And so we can do an experiment. We can plant in different planting days. And for example, we did that experiment here on campus, and we have one experiment in 1 year in St. Paul, 2023. And we plan during different planting dates. We control almost everything but planting date. And we have this. We have this response. It's nice. We knew that we expected this kind of response. And if we have to put numbers here, we can see that until the end of May, in these really good conditions with irrigation, the yield depletion was 0.6 bushels per acre per day of planting day delay. So we can use that to decide when to plant or when to kill the cover crop because we need to plant. So it's really good data. Then we can see in this plot that after the end of May, the yield depression increased, and the average is 1.5 bushels per acre per day in this experiment. And this is great. And someone who is trying or thinking about double cropping maybe can find this information really useful, besides the shape of the curve. So the numbers. The question is, this is one experiment, one location. The question is, how is going to be next year?
And at St. Paul.
Exactly. Or how is going to be next year in Huasica or at Huasica. And it's really hard to extrapolate this one experiment or generalize this. So we can go to the processes. There is a tilt in the axis of the Earth. Because of that, we have seasons. Because of the seasons, we have these patterns in radiation and temperature. And so when we are delaying planting date in soybeans, we are shortening the critical stages, the reproductive stages, and we are pushing them to the fall. So we are going to have less radiation. We are going to have less temperature to transform the radiation in biomass. Less grow in those stages is less yield. So we are going to have less yield when we delay planting date because we are going to have less incident radiation and less radiation use and less temperature that is going to affect the radiation use efficiency. And if we check these two variables, in this case, radiation and temperature, this is 25 years, the last 25 years, we are going to see that even radiation and temperature are variable. Imagine rains. But so the gray shades are showing us for each day of the season, the variation that we can expect in radiation and temperature for this 25 last year. So 1 year is, the conditions are never the same. So it's really hard to extrapolate one experiment to the future or to other areas. That's the idea. So what we can do? And we can do 25 years of experiments. And this is one unique case. Bruce Potter, he did this, 25 years of experiments conducted at Lamberton, Minnesota. every season during the last 25 seasons, he conducted an experiment like our experiment here in St. Paul. A really unique, worldwide unique data set. And he arrived almost to the same conclusion. So you have the numbers here. We have problems because we can have the absolute yield because the genotypes change during the 25 years. So the yield potential increase. So we can only talk about relative yield, but we can transform this in yield as well. But so the issue is that, okay, so then if we are going to change management practices and we want to quantify the response, we have to wait for 20 years, 15 years, 25 years. It's too much. So, and even if we do that, okay, let's try something new. Let's do interrow spacing, 25 or 20 years of experiments. The question is, can we extrapolate this to Huasica, to Grand Rapids? And probably the answer is no, because everything is changing as well. So that's
plus we have changing weather, right? We know that the weather's been changing. There's either climate change or things have been different. So we've got 25 years, but 25 years going back, we have very different kind of weather conditions 25 years ago. We need 25 years, but those past 25 years may not even give us a good idea what next year will do, even in this one specific location, Lamberton.
Yes, you are right. We are going to use the last 25 years as well in our model. So, but you are right. Your critique is also applies also to my approach, the approach that I'm going to present now. So, but that's good. We have another question there. There is a change. How it's changing, and how many years we should take to check this? Maybe it's better to take the last 10, not the last 25 or 20. But let's continue. So we have an alternative. And here is where the model comes in. We can use our data to validate, calibrate the model here in Minnesota. And we use it, for example, we have several models, but we are using this crop growth model for soybeans that is running in the DSAT platform, that is a really old but evolving platform that was developed in Florida. And you can see in this plot, this is the yield that we observe in our plots. All the experiments that 48 situations in which we change planting dates, cycles, interrow spacing, the genotypes, 2 years, so the climate was different. And this is what we observed. This is the average of our replications in the experiments. And this is the estimated yield, the simulated yield by the models. And you can see that it's not perfect. It's far from perfect, but I can tell you that it is improving, and we have more data from this last year, so this is going to improve. But it's really good. So the processes that we are simulating in this model are being successful in describing the relationships that are occurring in the crop and estimating yield. So our error was less than 5 bushels per acre in absolute terms. So if you agree that we have a nice model that exploits a wide range of situations, then we can say, okay, let's use this model to simulate or to check what would have happened the last 20 years in St. Paul. So we don't have 1 year anymore. Now we have 20 years for free. So it was not for free. We invested a lot of resources doing this validation calibration, but from now on, it's going to be for free. It's only some time in the computer. And here we have, or there you have, or there you are. Sorry because of my English, but we have the same shape. But you can see that there is a change in the response. So if we get the response that was provided by only one experiment, it was, for example, 0.6 bushels per acre, but the average response for the last 20 years was 0.4, so it's 50% different. And the same is here. So it's better for us to use this average than one experiment. And this can show you how this can change. And we are talking only about experiments that have been irrigated, so close to potential conditions. Imagine how this can change if we put water in the play. And the most important part is that, okay, and if we put now the weather of Huasica, and we have data from Huasica, so everything was validated with Huasica, then we can have the same for Huasica, and maybe it's different, and we can have the same from Grand Rapids, or from Crookston, or from Lamberton, and that's the trick of modeling. Ideally, if everything is working correctly and everything was calibrated and validated and the processes are working well or describing well the drivers in each of these locations for soybeans, we are going to be able to predict yields and how a management practice can change yield. And then we can start to talk about probabilities. It's not one more data. Okay, we are talking about the average, or we can keep the 75 percentile or the 25 percentile. We can start talking about risk. So we are in another level, comparing to one experiment or one data from 1 year, from one condition. We think that this is one of the most powerful. So this aspect is one of the most powerful. I don't know how to say. So it's a really good help for cropping systems, and so that's why we invested a lot of time, and we are trying to go further with the calibration and the validation of crop modeling. So we can start asking so how this can change interrow spacing, planting date. We have this for cycles as well, so we can ask what about this, what about that. So it's what if, and it's really easy if you have a good model to answer these what if questions.
Yeah, let me, if I just want to repeat, I mean, this is for fear of repeating what Aníbal's really clearly stated here. I'm going to just put it in my terms again, is that, that if we're talking about farmers have the option of doing their own experimentation on the farm, or they can take university information, or they blend those pieces of information. Ideally, the ideal situation is if either the farmer or the universities would do their research on every specific question on every single farm in Minnesota, so that we would have the data to say, okay, on your farm, seed treatments provided a 2.1%, or 2.1 bushel advantage, or narrow rows were worth 5 bushels, or planting a week earlier got you 2 bushels on your particular farm. We don't do that. We do a few sites here or there. We talk about St. Paul a lot. There's no farmers in St. Paul. So we're trying to extrapolate from what we do as the best we can. This is really the next level of this, is we could say, okay, we've done the work, we validated this model at a nearby location. Now we can go to your specific farm on your specific latitude, longitude, your soil type with its particular soil water holding capacity, and your historical rainfall patterns for your county or your township, and we can predict those same kind of things. And then Aníbal, in his last comment, I think is the most important piece, is then we can start layering on these other things. Okay, what if we did narrow rows and earlier planting? Do we get additional benefit for that? Or do we have some other option to retain greenness? If we get 1 more or 2 more days of stay green in the crop, does that do something for us for yield at the end of the season? So I think, we get benefits on a couple different levels from it.
Okay, thank you, Seth. And this has a lot the comment has a lot to do with this last idea. So this is the last. So we finished with planting date. I think that some of you were able to see the advantage of having a crop model that is working. So it's working, it's validated, no? Because the model is always going to give us a result. The thing is that the result is close to the reality. That's the question always with models. So we are going to see another aspect where models can help a lot. At least we think that, and this is trying to respond to answer this question, that is, how can we increase soybean yields? And this is a frequent question for farmers and for people giving advice at farms. And maybe there is one question that should be just before this one, that is, can we increase soybean yields? And to answer these two questions, so is can we, and if we can, how we can do this? And to answer or to work or to assess this question, we think that the yield gap approach is really useful. So I will spend like 1 minute to trying to describe this yield gap approach in case some of you are new to this concept. And what we are going to do is we are going to think in different kinds of yields. We can have the potential yield. What is the potential yield? Is the yield that we can have in a field when only radiation, temperature, and the genotype are limiting. So every else factor is plenty, is enough to maximize crop growth. For example, nutrition, temperature, no pest, no diseases, perfect management. Everything is perfect. No
irrigation.
So no water stress. So we have the potential yield. You can compare this, maybe a farmer that is irrigating and the management is everything is controlled. Maybe that yield can be a potential yield. Then we have the attainable yield. So it's the same, but now water is natural water. So it's natural rainfall plus the soil that we have that is going to interact with the rainfall. We can have a deep soil, we can have a shallow soil, we can have a very sandy soil that is not going to be able to retain the water. So we don't have the irrigation now. And most of the farms in Minnesota should be looking at this one. So it's attainable yield. What is the yield that we can attain with the water that we have? No, the radiation and temperature are also contemplated there. So that part is the same as the potential yield. And then we have the actual yield, the farmer yield. So and is the yield that your monitor is telling you that you are having in a farm, in a field, for example. And the difference in between the attainable yield and the yield that you are harvesting is the yield gap. And theoretically, is the room that we have to push yields. So, for example, if you are in a field and the actual yield is close or it match the attainable yield, there is no room to improve yield because you are producing according to the amount, maximizing the water use efficiency, and you are producing according to the water that you have. The water is what is limiting the yield in most of the unirrigated fields here. So the first thing so 2 years ago, we say, okay, let's try to check the yield gap that we have in the farms around Minnesota. So we started a project that was going to the farms, and we wait for the farmers to do all their things, all the management practices. When they finish it, we went there, we put some plots, and in these plots we had 3 treatments. So the control is the farmer management. We have another treatment that was, okay, let's put all the nutrients that we know the plant is using. So we went to the dealer and we asked for all the mixes with nutrients, and we put plenty of nutrients. We didn't check the expenses because this was an experiment. The only thing was be sure not a nutrient is limiting yield. And then we had another treatment that was on top of this extra nutrition treatment, we put protection. So, okay, fungicide, no insects, no weeds, everything was perfect, okay? And then we say, okay, if there is room to improve yield because of these management practices, we are going to see a difference in between the control and these 2 other treatments. And so here you can see for these 19 fields that we visited these last 2 years, so I think it was 9 last year and 10 this year, in red is the control, the farmer. So we didn't do nothing there. Then we have the fertilizer in green, and then we have the fertilizer plus or nutrition plus a fungicide, insecticide. And as you can see, among the 19 experiences, we only have effect of our treatments, that wasn't the fertilizer, and then there was no more increase when we protect the crop, only in one. So this was a kind of surprise, but if this, what we can say now, we can say several things, but one thing is that if these farms or if these fields are representing the average condition of the farmers and fields across the state, then there is not too much room to increase yields. Maybe we should start thinking the opposite, where we can save, or where we can save to reduce expenses and maintain the yield. Then we can think about caveats. Okay, how about these two last seasons? They were above the average, below the average, thinking about rains, because if we are below the average, then the attainable yield is going to be reduced, and maybe the gap is there is no gap because of that. So, okay, what happened in a different year? And the other thing is, we explore the average farmer and the average field, and so we don't know. We try to be objective, and we select farms in different places, but 19, if maybe the sample is too small to think that there is, to generalize and say, oh, there is no way to improve yield in Minnesota because you are producing close to the limit that you can, according to the resources that you have. So that's.
So we probably need to move on, but I just wanted to throw out one other important aspect, bring it back to the modeling side really quickly, is that, these sites are really important for us in model tuning, validating the models and also tuning them to be able to determine, because we need to have more, boots on the ground data coming in to be able to validate the model is predicting these yields correctly. But also we need to know what's happening in the field, because if we get data from a field and we find that the yields were 65 bushels, we put that into the model as the attainable yield or the potential yield for that site. But we find out later that there was insects or weed pressure or some other issue that we did not know about, then that puts some bad data into our model. And so having these folks visit the fields and scout the fields and make sure that we're applying and have an unrestricted yield in these locations really is important for us to tune these models and improve the overall model.
Great. Yeah, really great. So, and we were talking about, okay, maybe the amount, the sample is limited, and we didn't explore all the environment, all the conditions, or the average farmer. Maybe farmers in several farms are below this intensification level. So then the models again can be a really interesting tool, and that's why we are trying to work with this. Is okay, we can use the modeling if we have a really validated model for all the cropping systems across the state. We can use the simulation as an estimator or as a tool to estimate the attainable yield, the yield that you can attain in your farm this year, last year, 2 years ago, 3 years ago, with your management, with your genotype, with your soil. And then we can compare this against your yield monitor. And then we have the yield gap. And then we know if the room that we have to increase yields, and if we don't have, if it still is the case that we don't have too much room to increase yields, okay, let's start to think in the opposite, where we can say we are going to save money from the expenses, and we are going to reduce the impact on the environment as well, for sure, because we are saying that, okay, maybe we are too high in the amount of P that we are applying or other inputs, no? And if we have room to increase, we can check with the models again which management practice is the one that is limiting actual yield from being the attainable yield. So we think again that crop modeling is a really nice tool to extend extend this approach across the state to different environments in a really objective way to try to think how we can increase yield at the farm level. And we are trying to work. We are working hard with this. So this after this last season, we put together a lot of data from different fields, so we have data to validate, calibrate. So we are working on that, and I think that soon we are going to have some estimations, at least for some big environments. So, like for example, this soil type in this area, we are going to start from like big areas, and then try to check against maybe not the yield monitor, but the yield that was informed by the county or by. We have to define that yet. So I think that this is another example which you can see how we can use crop simulation or crop models to increase or intensify our systems. And that's all from my side. So if we have to bring up some conclusions, what we see today, what we want to discuss today with you is that was how we can use crop modeling to make decisions. And the idea is that we can test different strategies or management or conditions without risk. So we can test this in our computers if we have really good validated models with data that we are gathering from the field or from really controlled experiments. And then we can decide what to do in the field. We can extend this insight across years, across location. This is a big part of this, of the power of this tool for agronomy. And then we can start talking about probability, risk, average. So that's another important part. So at the end, it's going to help us to optimize decisions, what to do next year, what to do if this is going to happen in this field, what to do in this field and what to do in that field, because the soil is different or because the slope is different or because we are waiting a different weather condition for some reason, or because we have a cover crop at the beginning and there is less water at the beginning of the season because of the cover crop. And then, okay, we have to plant soybeans and what to do. That's the idea.
Yeah, we're going to wrap up here, but I just wanted to re-emphasize this point about risk, because I think that's one thing that our universities and even the private companies haven't communicated well. We haven't had the tools to really do a good job communicating risk to farmers. We can show them what the historical yields were and things like this, but I think these tools are better. It's a better direct way to talk with farmers about future risk of doing certain practices or changing the way they do business. I think we can more clearly say that if things happen like this is the downside or the upside risk of these things. So with that, I thank everybody for hanging on here, and I hope maybe Angie can come on and help moderate some questions for us here.
You bet. So I had a question. So when you were showing that example, Anibal, with the 19 different locations throughout Minnesota over the last 2 years, where you were comparing the standard practices to adding nutrients plus fungicide, insecticide, etc. One of the questions here was about did you differentiate farming practices within there? Did you just let the cooperating farmers farm the way that they had planned to, otherwise, tillage-wise, using conventional or, broadcast injecting for other fertilizers that you weren't focusing on, etc.?
So we didn't ask the farmers to do anything special. So we try to find representative farmers. That is really hard, and maybe we are not working with them. But then we let them do what they need to do. And we didn't talk about that, but we know what they do. So some of they already applied fungicide, for example. And for sure, according to this data, everyone is fertilizing really good, or even more than so my guess is that they are fertilizing for these 2 years, they have been fertilizing more than they need. But yes, we didn't influence the decisions that they took, but we have all the information, how they manage the work. We have varieties, we have the tillage information, we have the planting date, we have everything. And everything was representative. That's something that is important. Everything was representative. According to, so no one of these farmers did any strange or weird thing. But it's really hard to have an average management. So everyone is doing something different.
Right, right. Especially when everybody's definition of conventional tillage is different, for example. So another question, so you had mentioned that impressive data set that Bruce Potter collected over those 25 years down in Lamberton. And you mentioned that, and maybe it was Seth that mentioned how, maybe those 25 years weren't necessarily representative of our climate going forward. I had the same question in regards to varieties. I mean, how many soybean varieties are there? I know that individual companies will license the same variety under different names to several different seed companies. So how many varieties do you feel that you need to test in any given environment in order to have a good predictive model for predicting what will happen going forward with varieties going forward?
It's a really good question, and maybe it's hard to answer. Regarding the Bruce data set, what he did is he took like in between 2 and 5 varieties for each maturity range, and he took the varieties that the farmers were using in that moment. So the varieties are changing all along the period that he evaluated. So sometimes the varieties repeat from year to year because the farmers adopted the same variety 2 years in a row, but sometimes he switched the variety because there was a new variety in the market. And this is one of the really hard parts of doing this 25 years experiment, because you can use the same variety always, because you are going to have, at the end, you are going to have an old variety. So that's another important part of the modeling. And then when you are talking about how many varieties or how many hybrids in the case of corn to use to arrive to a response or to an insight about any management practice, it's really hard. And it's the people that is working in management, like me, like said, and that we are talking, for example, in this case, planting date, we try to use the less because we want to save effort. But maybe if you know that you have really different varieties that are going to interact with the practice that you are going to assess, you need to include at least the extremes. For example, if you are talking about inter-row spacing, and you know that you have a variety that is very erect and other one that is more planophil, maybe you need to include both in your experiment or in your test, in your field, maybe in your strip in your field. In the case of in planting date, for example, we include different cycles. We know that there is an interaction with cycles, so these last 2 years we had a range of cycles.
Maturities.
Yes, cycles for me is maturity. I'm sorry. But again, we try to minimize. We only had 4, and maybe a guy that is working with genetics is going to say, okay, you need at least 8, and we are going to discuss a lot. But at the end, so we use only 4. We know that there can be there we can find interactions, but it's better to have something than nothing.
Yeah,
Right.
just let me jump in real quick, and then I know you have other questions, but I think, this is a good place where we differentiate a little bit with the industry in that, if you're Corteva or Bayer, you really want to have genomic or genotype or variety or hybrid specific models. So you can say, if you plant my variety A, you need to increase the population to 48,000. And if you, on this one, so that they can sell you a package of management and hybrids and inputs, right? And so
Right.
it's a little bit different aspect to us is we need to be able to be more general and provide farmer data. But honestly, soybean varieties differ so little in response to a lot of these things. Anibel's models are really doing things like how upright the leaves are and things like this, but our varieties are so uniform and we have such a bottleneck in the genetics that really the maturity group is really all we need to know. As long as the model understands this is an elite variety, that we're dealing with high yielding varieties and not some old specialty type for tofu or something like this, then the models will do a good job for us.
Yes, and we are using the models again to answer this, but it was a good point. In these models, we are not specifying the variety, the brand, or nothing, only the maturity. And they are doing a really nice job. So this can lead us to the conclusion that there is not a big deal with the brand or the variety. But for example, if you are checking, you have an experiment, and the experiment was done in a place where white mold is a big deal. Okay, then if you put a variety that was very susceptible to white mold, yeah, you have nothing. That's the problem.
Yeah.
So you need to know what you are doing, where or how the variety can be interacting with something that is going in your experiment, in your field, in your strip. That's the thing. So in our case, we know that we didn't have white mold, we didn't have diseases. So our only effect, for example, in the experiments that we did to validate in the model for planting date and cycle, were those planting date and cycle. Everything else was controlled.
So are you relying on the book values for maturities? And then also, have you looked at the interaction between maturity and planting date as the climate changes?
The book, yeah. So the question about book value is we're using the number that's provided by the company, and so we know that those could be a couple tenths off, but we're not doing independent testing to determine whether that was a September 28 or an October 1st maturity date on those, or whether it should be really a group 2.1 rather than 2.1. So yes, we're using the and we know that there's some flex there. But the big thing is that we want to make sure we're not talking about a 2.5 versus a 2 or a 1 versus 1.5.
And the second one was about climate change and
the interaction. Have you been looking at the interaction between maturity and planting date as the climate changes?
We have been looking at the interaction in between planting date and maturity, but we didn't include the expected change in climate in the analysis. Okay.
Yeah, but we're doing those same. We're validating a planting date, maturity trials, and we're doing those across the state, all the way from southern Minnesota to northwestern Minnesota. So we're changing the actual variables, the inputs, and then those can be utilized. You could then tweak. Moving forward, instead of using predicted or averaged values for environmental conditions, you could, Anibel could push in some buttons and say, okay, we're gonna increase temperature by 1 Fahrenheit or something like that, and you could get outputs that would, if you knew what the weather was going to be like next year,
Yes.
we could do anything you wanted, but nobody really has a good handle on that, I think.
Boy, my retirement would be all set if I knew what the weather was going to be like next year. So thank you very much, gentlemen. This was a complex topic. Talked about a lot of lot of variables, and you're do two different types of modeling. I imagine that the AI modeling has it's gotta be exciting, and yet when you don't really know what's happening behind the curtain, it's gotta be somewhat scary as well. And so I just wanted to thank you for your participation here today. For as a recap, as a wrap up, thank you again for attending today's program. If you'd like CEUs, we will be displaying those in a moment. You'll need to use the CCA app in order to get that CEU. And if you're having difficulty with the app, we can have you enter your full name and CCA number in the chat, and we can record that for you. But we obviously would prefer that you use the app. There's that short 3-question survey we'd appreciate it if you'd take. Thank you again to our sponsors, Minnesota Soybean and Minnesota Corn Research and Promotion Councils. And I just wanted to let you know that next week's program is going to be focused on managing weeds with more than just herbicides. We need to start throwing the kitchen sink at these hard to manage weeds. And so I expect that next week's program will be heavily attended as well. So thank you very much for your attention here today.